The next speaker is also online. This is Vito Squicciarini. I hope I said it right. From the University of Padova, Substellar companions to B stars, exploring the frontier of planet formation. Vito, are you there?
Yes, I'm here. Can you hear me?
Yep. Please go ahead.
Share my screen. Just tell me if you can see my screen.
Yes, that's right.
Great. Here I am. So, first of all, I want to thank the organizer for giving me the opportunity of being here today. My name is Vito Squicciarini. I'm a PhD student at the University of Padova. And today I will try to highlight how high-resolution astronomy is helping shape our view of some exotic planetary system and their formation. So I will start with the classical plot that you see so many times of exoplanetary sciences. That is something akin the Hertzsprung-Russell diagram for planetary system. And you see here that the distribution of confirmed exoplanets in this diagram is not random. It has some clear concentrations. And this is exactly the key idea of exoplanet demography. The idea that the phase space distribution of exoplanets bears the footprint of formation processes. And so our goal is to build a complete and unbiased planetary version of this Hertzsprung-Russell diagram by combining all the methods that we have. And here I have colored in different colors the different detection techniques. Now I want to stress to introduce another parameter that is the stellar mass. And I want to highlight a few interesting facts of the known exoplanets. To begin with, 90% of the planets have a semi-major axis less than 1 astronomical unit. So they are closer to their star than the Earth is to the Sun. And as a second fact, 99.3% of the known exoplanets are orbiting stars with less than 2 solar masses. And if we compare it with the frequency of high-mass stars, which I define as the stars with more than 2 solar masses, we can see that these stars are underrepresented by a factor 6 in the current census of exoplanets. So we might ask ourselves if this shortage of planets around high-mass stars is real, or rather if it is a selection effect. So you see that the different colors are proving different parts of the diagram, suggesting that every technique has its pros and cons. And for instance, transits are strongly biased toward the close-in exoplanets. And the same applies also to radial velocities to a certain extent. And we know also that microlensing is mostly sensitive to a short range of separations, and that direct imaging is the technique that goes to the other end, so to wide exoplanets. And then there is also the observational tendency to observe to target low-mass stars in surveys. So what do we really know about planets around high-mass stars? I will show you a recent result of Voltov et al. That studies the occurrence of giant planets and small brown dwarfs around evolved stars. And you can see a clear trend with the stellar mass. Just focus on the blue lines here. You see that the occurrence increases with stellar mass up to 1.7 solar masses, and then it goes down, falling to about 0 at about 4 solar masses. Then there is a positive correlation with the metallicity of the occurrence, and there is also a well-defined peak of the separation distribution. But as I told you before, the radial velocity technique is blind to wide exoplanets, and we can expect that if we increase the size of the planetary system, at some point the interesting separation where giant planets are thought to be present is outside the sensibility region of radial velocities. So this is where direct imaging comes into play, because it can complement the radar velocities in two ways, by exploring the other regions of planetary systems, and also by studying the young phases of planetary formation. And in this way, we can study also, we can discriminate between different models, because different formation models do make very different predictions about the existence and the occurrence of giant planets around this kind of stars. So here I introduce BEAST, that is the survey which I will talk about. It's a direct imaging study that we are performing with the sphere at VLT, and its scientific case is to look for substellar companions to 85 young P stars in the Scorpius-Centaurus association. And you can see in the right that it is really the first effort, direct imaging effort, to study this kind of stars. And then we are at about 1/3 of the survey, but we already have some interesting results, because just to go back to the previous plot, you can see that the sensitivity window of BEAST has just one planet there, one known exoplanet that is actually the first BEAST discovery. So it's really proving a new part of this diagram. And this planet is BSNB. There's a recent work by Jansson et al. And this planet has been found around a binary system with a total mass between 6 and 10 solar masses. And you can see that it is very farther away from the star, from its star. And you can see that it is really something we did not expect to find, because we expected to find a closer planet in a sense. So it came out as a surprise to our team, but we could confirm the moving motion, the common proper motion, because we had 2 epochs at hand and a third archival epoch from the year 2000. And so we could really confirm that this object is bound to the BSN system. But we asked ourselves if a capture scenario could be used to explain the presence of this planet, because if it turned out to be the only case throughout our whole survey with a detected planet, it could be an unlikely capture of an object that formed elsewhere. But then we had another discovery, the second discovery of our survey. We called it now REVA. That is an invented name because it's still under review. But the important fact is that it is a 14 Jupiter mass companion around a massive star. And it is, you can see here that its properties are quite similar to those of BSNB in terms of mass and also in terms of separation within a factor 2. And also the total system mass is more or less the same. So this gives the idea that the occurrence of this kind of object is no zero, is higher than 0. But there is also possibly a third detection in the same system as REVA. We have identified an interesting source at about 0.1 arc second from the star. So it is really near the coronagraph edge. So we are not able to confirm or reject its existence, but we are looking to do a follow-up in the future to understand if it is real or not. But if it was real, it would be another 20 Jupiter mass object. But what are these objects? Are they giant planets or small brown dwarfs? We don't know, because if we use the classical boundaries that divide planets and brown dwarfs, we would say that BSNB is a planet and REVA is a brown dwarf. but of course their similar properties argue for a similar formation process. And indeed, if we look them not with their mass, but with their mass ratios, that is the ratio of mass versus the stellar mass, we see that these objects are more similar to Jupiter than to brown dwarfs that are found around solar mass stars. And this leads us to discuss the formation scenarios of these objects, because there are essentially two main processes that explain giant planets in other systems, that are co-accretion and gravitational instability. And co-accretion is a bottom-up process which preferentially creates small planets that are close to their stars, at about the distance of the snow line. On the other hand, gravitational instability is a top-down, a binary-like process that can create a flat mass distribution of brown dwarfs and super Jupiters at wide distances. And the difference, the key difference is in the occurrence of these planets, because co-accretion requires a turn-off, as the one observed in radial velocity studies at a mass higher than 2 solar masses, while gravitational instability does not require, is not dependent on the mass or weakly dependent on mass. But there are challenges for both models. Neither of them can fully explain our observation, because a co-accretion scenario is very difficult due to the fact that the formation timescale required is much higher than the disk lifetime around these stars. And also they are very wide away, farther out from their star. On the other hand, gravitational instability usually has a much higher conversion efficiency of disk mass into companion mass. And so it is strange to create such small objects compared to their stars. But the key aspect is that both models have never been extended to this regime of stellar mass and also disk mass, because we had never found objects like those before. So just to wrap up and to give a few prospects for the future, interferometry can be crucial in the future to follow up the results of our survey, because for instance, with gravity, we can confirm or reject the inner candidate of the REVA system. On the other hand, both direct imaging and interferometry can give us a better astrometry of these objects, and they can help determine orbital parameters, giving hints on formation and dynamical evolution. And then it is important also to have a spectral coverage of these objects, because measuring, for instance, the CO ratio can give us a glimpse of the primordial orbital location, and also a comparison with James Webb, with the observation that James Webb will perform of free-floating brown dwarfs and planets will tell us if there's a difference between these objects and field brown dwarfs. And so with this, I end my presentation, and I thank you for your attention.
Any question from the audience? I have a question, a simple question about the snow line. What distance is the snow line on this B star? And I guess you can resolve the snow line with an 8-meter class telescope in this case, which is a huge advantage of this class of star.
Well, okay. It depends, of course, on the scaling of the snow line with the irradiation that is not clear. It's not clear if it goes with exactly with the separation or with the square of the separation. There is some discussion in the literature. But in any case, it would be at about, let's say, 200 astronomical units, 100, 200 astronomical units for those planets. So if I understood correctly the question, these planets would be outward of the snow line. But maybe I've lost some part of the question.
Yeah, I was wondering, not the position of the planet, but more the position of the ice line, the water ice line. What is usually the scale of this, of the position of the snow line, ice line?
Okay, so I've already answered to this point.
Thank you. Any other questions or online questions? There is a question from René Ottmeyer. Can you tell us about the multiplicity in your sample, the stellar multiplicity in your sample?
Okay, well, our sample, in a sense, is biased against binaries because we have excluded by design non-binaries that have intermediate separation. So every time we had B stars with the companion that would be within our field of view, we excluded them. So in a sense, our binaries are either very strict, very close binaries like Bsen, or very wide binaries with a very weakly link, like, for example, HIP 63003 and HIP 63005. So I don't remember exactly the fraction of binaries in our sample, but in a sense, we have less binaries that in a sample that is taken randomly, because it would have affected negatively the quality of our observation. But it is indeed important to see if systems like Bsen that are close binaries and systems like the one of Reva that is a single star have different properties. And the fact that we have found two similar systems in a single system and in the binary system is important in our opinion.
Okay, thank you, Vito.
You're welcome.